Okay, got an angled projectile, 37 degrees, and it's being kicked with a velocity of 20. This is our v total. It's the velocity that's going at 37. Now that's going to change as time goes by because little g is changing that. Okay, we want to make one of our tables. So let's see, where do I want to do that? Let's do that over here. Independence of motion, horizontal and vertical are separate. Okay, and for these we like to draw a picture. So let's go over here and show that. Okay, this is 37. It's that angle with the horizontal. This is 20. That's the magnitude of the velocity. Okay, magnitude and direction. So we know it's a vector. Okay, and we want to calculate the maximum height. So we care about this point. We don't care about this over here yet. Okay, we want to know how high it goes. All right, so let's list what we know. Vertically, we have an acceleration equal to negative 9.8. Okay, what do we know about the vertical velocity at the top? It's 0, just like if we throw a ball straight up, okay, the vertical velocity is still 0. So we're gonna call that a v final for y, and it's equal to 0. Okay, and I think that's all we know so far, until we do a little bit of trigonometry. Okay, so let's take this vector and let's kind of blow it up over here. Okay, that's 20, that's 37, okay. And so we're going to do 20 cos 37. We're going to do 20 sine 37. And let's do some calculator clicking. Okay, that's another common mistake, is mixing up x and y in your chart too. That's another one we could add to our mistakes on the other side, mixing up x and y. Okay, so sine, that's y. So we're going to say that's v initial in the y direction is equal to 12. We'll round to 3 sig figs on this. Okay, and then for simplicity, we're going to go up here and we're going to round this to 16.0. Okay, that's going to be Vx. Okay, now again, if you're doing a UT homework, you don't want to round that much. Okay, I'm just doing this to make this a little cleaner on this page. Okay, they'll come out very close, but need a little bit more accuracy when doing UT. Okay, now what do we want to find here in part A? It says maximum height, but what do we call that in our variables? We call that a delta y. Okay, delta y equals question mark. We don't know it. Okay, now doing this, we could find any delta y on here, okay, at any point. Okay, we want this special one maximum height. So on our diagram. Here's delta y. Okay, now you notice here we don't have what? We don't have time, okay? We have a special equation for when we don't have time. It says this, VF squared equals VI squared plus 2A delta y. Okay, let's rearrange this first instead of just plugging numbers in this time. We want it to say delta y equals. So first I'm going to subtract that to the other side. VF squared minus VI squared equals 2A delta y. Okay, now what do I do? Divide by 2A. So I'm going to say delta y equals, okay, and then I'm just going to write this divided by 2A. Okay, let's plug in some numbers. This is all y stuff. Okay, we ignore this side of the table when we're using any of these equations. Okay, so we're going to use this side. So we've got 0 squared minus 12 squared over 2 little g's. Okay, and you square it before you subtract it, by the way. Okay, so that is going to eliminate our negative signs. All right, so we do 144, that's 12 squared, divided by 2 times 9.8. Our negatives went away. Okay, so this thing's going to go 7.34 meters high. All right, 7.3 meters. Okay, that's going to be our maximum height. Okay, questions on that? Okay. Let's do one more part at least together. All right, the time of travel before the football hits the ground. Okay, we're not talking about this point anymore at the top. So we do kind of need to make a whole new chart. All right, it's kind of a pain, but it doesn't take that long. So let's do it. Horizontal, vertical. Since we're talking about a different time and a different point in space, we really should probably do another one. Okay, some of these things are going to stay the same. Vx is still 16. The launch velocity is still 12. Well, let's do acceleration first. Acceleration's negative 9.8. Okay, the launch velocity is still 12. Okay, but we are way over at this point here. Okay, and so if it goes up at 12, what's it going to come down at? Negative 12. Okay, Bryn? Can I what? Is that better? Is that good? Was I off the screen? I have this little screen here. I think they match. Oh, they don't quite match. Okay, so this is going to be V final in the y direction equals negative 12 meters per second. Okay, now anybody see another way to do this? We're going to use that to solve for time. What's another way we could deal with the velocity here? There's usually more than one way to do physics problems. What could we say the velocity is here? 0, and how much of the total time is this? Half. So you could, a lot of times people say this is 0. They'll find the time to here, and then we just have to double it. You can do it that way too. Okay, this will get you the time without doubling it. Okay, t equals question mark. All right, and we have this. We have that one we can use. And if we arrange it for time, we have t equals b final minus b initial over a. Okay, plug those in. And let's see what we get. I just been going one past the decimal and everything. Okay, so we get 2.4 seconds for the total time travel. All right. Okay, how far away does it hit? Okay, now what direction are we talking, X or Y? We're talking X direction. I'm not going to redo a whole chart. I'm just going to say this. I'm going to say Vx equals 16. My time, I'm going to keep a little bit of accuracy here. I'm going to say 2.45 so it doesn't throw my answer off too much. Okay, and we want to find delta x. This part's real easy. Horizontal, super simple. There's only one equation you can use. On your equations page, it looks like this. Okay, if we want to find delta x, it looks like this. And so it's just multiplication. 16 times the 2.45. And we get 39.2. Okay, and that finds the horizontal range. Okay, questions on any of those first three? If I just put that up at the start of the class, would that freak you out a little bit? Maybe. Okay, doesn't that look cool? Are you guys proud of yourselves for understanding that? Maybe you don't totally understand it yet, but that's okay. It might take doing a couple of these on your own for you to really get it. Okay, but look how cool that is. Look what we just did. Are you guys pumped? Okay. Come on, it's Halloween. All right, the velocity vector at the maximum height. Okay, let's just, this is easy. We're not going to really have to do much here. Okay, let's draw the velocity vector at the maximum height. Okay, there's the point. I've been using red for that. Okay, so it is only going horizontal. All right, and how fast is it going? 16 meters per second. Okay, it's just equal to our Vx. Okay, that was easy. Part E, the acceleration vector at the maximum height. Let's draw a parabola yet again. Okay, if we're asked to draw the acceleration vector, or say what it is, we're going to draw a dot. That represents the football. The acceleration is down, and it is negative 9.8 meters per second squared. Okay, what's the acceleration vector here? Not difficult. It's negative 9.8. What's the acceleration vector when it is sitting on the ground before launch? 0. Okay, it's still sitting on the ground, not a projectile yet. Okay, what is the acceleration vector as it is bouncing? That gets tricky because during the bounce it is in the process of changing its velocity, turning around to be some upward positive crazy acceleration vector. Okay? But anytime it's a projectile, it's in the air, gravity's acting on it, it's negative 9.8. Okay, Tim? Never mind. Okay, that'll